I can say I miss factors of 2 here and there, and for obvious reasons, deal with it. I'll drop the view, and you'll say, you dropped the view index, and I'll say, you should know it's there, come on.
And I feel like I accepted the comment. It even makes more sense, but I still don't know. I mean, yes. I don't know. I feel like I can accept it.
Do you think lectures like this will be lectures versus going too fast?
This is something I can accept.
I feel like it would be more useful in this kind of context. Not sure, but like a long derivation like that where they're not asking.
I don't have the final explanation.
Oh yeah. I mean, I wrote down everything that I know. I don't. What is grasshopper?
Yeah, so let's start again with our second lecture today with Natalia of intensities for dark sectors.
All right. So yeah, I decided to switch things up a little bit. So yesterday I told you the plan was visible dark photons decaying to the standard model first, and then dark matter through dark photon portals for the second 2 lectures. But I think I'll be able to reuse a lot more and sort of introduce things as we go if I do finish off visible and invisible dark sectors at B factories today, and then move on to fixed target experiments with, again, the full broader scope tomorrow, which actually makes sense now that Philip's finished talking about all of the theory for the dark matter models as well. So I wanted to start by coming back to, I think it was your question about the Babar detector. Just show a little schematic. So it is quite similar to Atlas or CMS conceptually in the sense that it has a silicon tracker on the inside, a less precise tracker, a drift chamber in this case, not straw tubes like Atlas. So in that sense, it's kind of Atlas-like. And then an electromagnetic calorimeter. There's one new detector sandwiched in there that you don't see anymore at high energy colliders. It's kind of interesting, which is a Cherenkov detector. I was reading about this in the Babar instrument paper, and it's actually super cool. So the idea is to image Cherenkov rings in crystals, but then they actually use total internal reflection to bring the Cherenkov light into this big water tank where they image the cones and reconstruct them, and that lets them tell whether a particle with GeV scale energy is a kaon or a pion. So this is the Babar version of particle flow at GeV energies. Of course, it doesn't work at a TeV anymore because they're both traveling too close to the speed of light to leave a Cherenkov cone with meaningful differences in angle. But it's very useful at Babar energies. And then they don't have a hadron calorimeter. They're IDing individual charged hadrons. They have what they call the instrumented flux return, which is like a muon system at Atlas, so lots of layers of steel to get particles to interact, and then instrumentation as you go in the same region where the magnetic field is. And that lets you ID neutral hadrons, but not measure their energy. So pretty similar, a little bit different. And also 3.5 meters long, to be contrasted with the sort of cathedral scale of the LHC detectors. Okay, so I think we're gonna go back now and try to understand this dark photon constraint from Babar, which is shown in pink on this slide. And here are some of the papers from their actual analysis, some of the plots from the actual analysis paper from Babar. So I was sort of telling you earlier the basic process that we're looking for is E plus E minus to a photon and a dark photon that either goes to E plus E minus or to mu plus mu minus. They looked in both. The details, differences between them won't really affect what I'm going to say. With a cross section that goes like 2 pi epsilon squared alpha squared over ECM squared times some log factor related to the angular coverage of the detector, which is of order 4. And when you multiply that in by the luminosity to get a total yield, that gives you something that scales like epsilon over 10 to the minus 3 squared. Luminosity in units of inverse attobarns, which is order 1 for the full Babar run, times 10 Jev over ECM squared times 1,000 events. So that's the scale of signal that we're talking about. And you can see the background binned in fairly large energy bins. Over there, you can also see, by the way, what a big resonance looks like. This is the J psi going to mu mu, that little green bin that's elevated. So that's a resonance that doesn't have any epsilon suppression. And that's what it looks like over the background in this core spinning. When you make your resonance a factor of 3 orders of magnitude smaller, you're obviously going to need to zoom in a lot more in order to see anything. And you can also tell, okay, looking for a little BSM resonance on top of the J psi, that's going to be pretty hard. So there's in all of these sensitivity plots, when you look closely, you'll see these individual places where the sensitivity just disappears. And that's usually because you're right on top of some standard model resonance and can't possibly hope to find some teeny tiny resonance on top of it. So how do we look for 1,000 events over this background, which is on the scale of like 10 to the 5 events per 100 GeV, per 100 MeV bin? Well, clearly that's going to depend on 3 things. It's going to depend on your resolution for the invariant mass of that E plus E minus or mu plus mu minus pair. It's going to depend on your signal over square root of background within some bin. So I'll call this sigma m. Bin of size sigma m. Signal over square root background gives you the statistical sensitivity. And then the third item is fit systematics. The gist, so I want to talk about all 3 of these. Fit systematics is in some sense the last logical thing to talk about, but I want to quickly get it out of the way because it's relatively simple to understand why it's order 1. Not relatively simple to deal with in an experimental analysis, but relatively simple to understand why it's an order 1 effect. Which is that if your background is slowly varying on some range of masses that's large compared to the resolution, so I'll say this is, each data point is roughly like 1 mass resolution wide in this binning, right? You can fit smooth curves to it. There's some uncertainty in the normalization of this curve in a given bin, but that's driven by the fact that in this window you have statistical uncertainties. And in fact, so as long as you can build a window where the number of points is large compared to the number of model parameters you need in order to fit the data, then the uncertainty in the prediction for, let's say this is my signal bin. I want to look in this bin. Then my prediction for what the background should be in this bin, based on that fit, has a smaller uncertainty than the statistical uncertainty on one bin. And so that's the way these searches are always designed, to find just a number of bins. This is actually a crude version of it. Usually, a lot of these are actually done as unbinned likelihoods with a signal plus background fit, and then a background only fit for a null hypothesis, et cetera. but at a sort of crude level of understanding the statistics. As long as the number of bins is greater than the number of parameters, I should say number of bins minus 1, so the number of sideband bins, that implies that the systematic uncertainty should be smaller than the statistical uncertainty on the number of background events in the signal bin. And so then your sensitivity to how big a signal you can see there is set by the statistical uncertainty on that bin, which is just the square root of the background in the bin. So that's all I'll say about fit systematics, that they can be usually made a less sim order 1 effect. Yeah?
Two questions. I see on the plot there that they compared data to Monte Carlo. Did they use the Monte Carlo prediction, or was it just a purely...
They didn't. This was to show that they have some clue what's going on in the detector. And you'll see there's actually a pretty bad discrepancy down here at really low masses in electrons. I think that turns out to be dominated by conversions of photons in the detector material, which they didn't include in their Monte Carlo. But yeah, they were always just doing fits in the window. And that's what's usually done in these very narrow bump hunts, just because you are sensitive to small shape discrepancies between the Monte Carlo, between the simulation and the data.
And then, sorry for what you said, this but did they use the photon being emitted?
They are looking for the photon in the final state. Yeah.
Right, but does the dark photon signal have different photon kinematics than the standard background?
So the standard model, so yes, it can. It can. Let me come back to that later. So yes and no. So actually, let me come back to that right now. That was kind of the next thing I was going to talk about. But it might not immediately appear to be, yeah, I'll do that before the mass resolution. OK. So this is the second board. But I think I'm going to need more board space. So let me pull this side up. I'll try to write big for the people on that side of the room. And please holler, thanks. Please holler if I fail. So let me just give 2 examples of background processes for electron final states. The first sort of dumbest thing you might write down is it's just the same diagram, but with a virtual photon instead of the dark photon. So, but you can also worry about things like another important one is radiative Babar scattering. So the electron and positron just scatter off each other, and one of them radiates off a photon. That could generate the same final state. This has very different overall kinematics. It's peaked with the E plus and E minus being kind of in the final state being close to the beamline, and not necessarily that low in invariant mass. So it tends to populate the higher invariant mass zone, but also it has different kinematics between the E plus and the E minus than a high invariant mass dark photon would, which tends to be more centrally produced in the detector. So you can reduce things like this with kinematic selections on where in the detector both the photon and the E plus E minus are. This diagram, on the other hand, you can see that for gamma star, for pair masses comparable to the E plus E minus, to the dark photon mass, that part of the mass distribution, everything else in the diagram is identical. All the like this propagator is the same. That vertex is the same. So the photon kinematics is going to be exactly the same. The E plus E minus position in the detector is going to be exactly the same distribution. And there's no kinematic way that you can reduce this. So this is a kinematically irreducible background, by which what I really mean is that anywhere differentially in phase space that you look for that, it will always have the same ratio of signal to background. And it turns out in most experiments, or at least in many experiments, because you can cut away from everything else, unless you have other backgrounds that are parametrically enhanced compared to this one, this background is a good order of magnitude estimate for what your total background is going to be in a given mass window. So you can't make it any smaller. And this irreducible background is typically, I'm saying the total background in a well-designed search is typically less than order few times this irreducible background. So what I mean by a well-designed search is kind of the things I was just, so first of all, if you have other backgrounds that have different coupling counting, then those are obviously, if they have fewer powers of alpha, they're obviously going to dominate. I already gave you the example that this has some extra log enhancements at certain parts of kinematics. You have to cut away from those kinematic regions in order for my statement to be true. But once you go to kinematics that doesn't have basically any large kinematic ratios, if everything else has the same coupling counting, it's only going to enhance the background by a few relative to this one diagram, which is this irreducible background estimate. And it turns out that the signal over irreducible background is actually something that we can calculate pretty straightforwardly, because it's literally the same diagram. The only difference is the propagators, yeah?
Are there other well-motivated BSM processes that could produce this final state also? Or are we pretty sure that if you have this final state, it's either going to be the dark photon or this virtual photon?
So for this specific case, I think it depends on how detailed you make the final state. And what I mean by that is, for example, a lot of Babar's time was spent on resonances of upsilons, on upsilon resonances. And there is an upsilon decay that would look similar to this, but with a different diagram where it's basically an upsilon decaying photon and a light Higgs. That was actually what motivated the very first incarnation of this analysis. But it's easy to tell the difference if you do see the signal, if you just run on two different upsilon resonances, or once on resonance and once on the continuum, and you see different signal rates. You could ask, could I put something else into this diagram and get roughly the same yield? If I put in a dark Higgs, say, something with a coupling proportional to standard model Yukawas, you're not going to see something in an electron collision that you wouldn't, in 2-to-2 electron scattering, you wouldn't have seen first using B quarks. Right, so I'm now talking about something that you don't see associated with the resonance, but really in the continuum. On the other hand, if I had a U1B minus L gauge boson, it could produce this too. If I had a, electron number minus muon number is also anomaly free. If you wanted to gauge electron minus muon number in the standard model with a small parameter, that would certainly give you this signal as well. Yeah?
Naively, I would think the non-zero master mediator signal would change your E plus E minus kinematics from this.
Absolutely. So what I really meant was that D signal dme plus E minus, thank you, is equal to D background dme plus E minus, this ratio. So for this, what I'm going to do to make this relationship more explicit, I actually want to, I've been using the narrow width approximation for that A prime, but I want to really think about that as a propagator that I'm putting into the diagram, and then I'll integrate over my resolution limited mass window to get a signal in a background. And what theorem here that I can relate the ratio of the rates to the propagators squared, that's really true differentially in mass and differentially in as many other kinematic variables as you care to include. It's true of the fully differential cross-section. You can integrate over everything else if you want to. So really what I'm saying is that d sigma background, if I take d sigma background, d me plus e minus, after I've integrated over the phase space after my cuts, let's say that's some function, f of me plus e minus. Okay, and this f should be slowly varying away from the threshold, right? Away from me plus e minus. There's no other kinematic scales in the problem. This should be a fairly smooth function of m. So that's what I mean by my d background irreducible. So, sorry, and what I mean here is I'm integrating over all of the phase space variables except me plus e minus. So my denominator here is just f of me plus e minus. My numerator can be obtained from this differentially by just replacing a virtual photon propagator with a dark photon propagator. So that means it's, again, f of me plus e minus times, oh, and I also have to replace a photon coupling with a dark photon coupling. So I'm going to have a coupling epsilon e rather than the photon coupling e in the amplitude. And then I'm also going to have a propagator that's me plus e minus squared minus ma prime plus 2I gamma a prime squared. And because I'm trying to write this differentially in e plus e minus, I need to keep track of the width of the dark photon now. I'm dividing that by the propagator that I had in the background process, which was just me plus e minus squared. And then this whole thing gets squared because I'm trying to calculate a cross-section. So I need to take the mod squared of the amplitude. So these f's cancel out. Any questions on what I've just done? OK. OK, so now I can integrate. Sorry, what I actually wanted to take a ratio of was not the differentials, but the integrals over this mass bit. So I'm going to integrate this over some mass window delta m on the numerator and denominator. And the denominator, that'll clearly just give me a delta m prefactor, assuming f is slowly varying and delta m is much less than m. The delta m that I'm thinking of here is something of order the mass resolution. And the numerator, I'll have to integrate that function. So my S over B irreducible in the bin is going to equal 1 over delta m times the integral dm over the same delta m window. I'll have epsilon squared and I'll just drop the e plus e minus subscript. I'm going to have m to the 4th over m squared minus mi prime plus I plus 2I gamma a prime squared mod squared, where this integration is averaged over m equals mi prime. So for m equals MA prime plus delta, I can linearize the denominator. And you can see that the MA prime fourth terms are going to cancel. So I'll get m to the fourth over, I get a 2 MA prime delta minus 4I MA prime gamma. I'm sorry, I screwed something up here. This should be gamma over 2, so that the width, when I square this, I actually get an m gamma term. So apologies for that. I end up with a 1I MA prime gamma mod squared, plus terms that are quadratic in deltas or gammas. And that just simplifies to MA prime squared over 4 delta squared plus gamma squared. So that gives me this thing here is actually a function that has a peak value when delta equals 0 of MA prime squared over gamma squared. A width of gamma, which is much less than this delta m window, which means I can go ahead and, in fact, the contributions outside of delta m don't matter. This is really dominated by the resonance peak. And that gives me 1 over delta m times epsilon squared. I'm sorry. Yeah, I made this mistake the first time I did my notes too. Second error. In the signal diagram, there are 2 epsilons. There's an epsilon at this production vertex and at the decay vertex. So in the amplitude, I should have had an epsilon squared. And when I carry that along for the right, I get an epsilon to the fourth here. And you might be asking, I had a cross-section that scaled as epsilon squared before. Why do I have epsilon fourth all of a sudden now? Well, I'm going to have this extra MA prime squared over gamma factor from integrating this width. And that gamma, you might remember, was a third MA prime alpha epsilon squared times this number of degrees of freedom I can decay into. And so one factor of mass here cancels. I'll keep track of my 1 over a delta m. And I end up, yeah, there's also a 2 pi factor, I think, that comes along from doing this integral carefully. Maybe it's just yeah, it should be a 2 pi. And that gives me I'm sorry, just a second. A pi over 2. It gives me a 3 pi over 2 alpha, an overall factor of epsilon squared. And I can put my n back down here as well to keep track of it. Epsilon squared times the ratio of the A prime mass to this window you're integrating over. So that's a solid estimate for what the signal over background will be in a band of width delta m. And again, usually the background is going to be a factor a few larger because you have to account for other processes beyond the one that I have there. but this sets the scale. So if I write signal over square root background as the square root of signal over background times signal, remarkable math there, I know. I've got an estimate for this, and this is just the yield calculation up there. So we're close to being able to estimate the sensitivity of this experiment, except, of course, that we need to know about the mass resolution. So I wanted to try to give a little bit of intuition. Any questions first before I move on to resolution? OK. So I wanted to try to give a little bit of intuition about where the mass resolution of detectors comes from, because it's often presented as like, well, you know, experiments work really hard to optimize their mass resolution, and then they plot that resolution in a paper. And sometimes you don't know, like, is the scale, usually they've worked hard enough that the scale isn't limited by how hard they've worked. It's limited by some intrinsic physics of the detector. And so I want to just talk about what are those intrinsic physics sources of resolution that, and how you can estimate what the scale of resolution you're going to get is from that. So I'm just going to do this for an idealized case, though, where I have, say, my dark photon produces some E plus E minus pair that's fully transverse to the beamline. And it's going to go through some layers of tracking material. And this dark photon is pretty boosted. Got 10 GeV center of mass energy. Typical energy that that dark photon is going to carry is roughly half of that. You know, transverse part could be 3-4 GeV. We're thinking about dark photon masses for the most part in the 100 MeV scale. So this is a pretty small angle process. If one particle, if each has an angle theta 1 from transverse, the other theta 2, momenta P1 and P2, the mass of the E plus E minus pair is roughly given by the squared is given by something like this. So if I assume comparable masses and angles, I'm just going to say it's of order P1 theta, P theta for the individual particles. That means that the uncertainty in the mass resolution is going to look like the momentum resolution times that opening angle theta added in quadrature with the angular resolution times those characteristic momenta. So this angular resolution is set primarily by two effects. One is that each of these sensors doesn't have infinite position resolution. They're around the resolution of a silicon strip detector in the transverse direction is around 20 to 50 microns. I think they got down to 20 microns. And they put these trackers very close to the beamline, a characteristic separation between the interaction point and that first layer, I'll call it L, is of order 10 centimeters. Yeah?
This is a super naive question, but if we can assume this positron and electron coming off are going in straight lines, couldn't you just look farther away to get a more accurate measurement of your angles?
So you can, except that the second contribution is that you're going to have multiple scattering of that track in each detector layer as well.
Got it.
The farthest layer of this really high resolution silicon, by the way, is at like 20 centimeters. So it wouldn't change my estimates that much. But yeah, you should sort of think about, you can think about first layer, middle layer, et cetera. That's a good point, though. So this gives you a scale of angular resolution that's going to be roughly like a sigma theta at the 5×10 to the minus 4 level. And the other thing is you can use multiple measurements to improve that uncertainty, right, by averaging them together. But again, you're still stuck with the fact that there could be different multiple scattering in each layer. And so you have to deconvolve that. And so that's the second part. So this is the sigma theta just for measurement. But there's another sigma theta from another contribution to the angle uncertainty from multiple scattering in the first layer. Once you've multiple scattered in the first layer, you can't know, and then you'll keep multiple scattering in later layers. And there's just some intrinsic uncertainty about how should I point back. So that multiple scattering gives you an angular resolution that's it really gives you a momentum-independent transverse momentum kick. So the angular effect is going to be that characteristic angular momentum kick, which turns out to be 13.6 MeV times the square root of the thickness of the layer and radiation lengths. This tends to be about 1% for a typical silicon detector, 2% when you add services. That's the scale, divided by the total momentum. So you can see this is actually, if I put in 1%, just because it makes the math easy, that's an MeV. That's going to give you a 10 to the minus 3 radian resolution. For P of order a GeV. This piece gets better at higher momenta. So you can end up in a case. So these are kind of comparable, if for the momentum scales of interest at 10 centimeter distances. That's why there's not a lot of incentive for Babar to go in and make like a 1 centimeter away tracking layer, because they drive this smaller, but they're still dealing with GeV scale momenta, where you're going to have multiple scattering effects in that layer that are bad. Okay, so that takes care of the angular resolution. And now I realize I've planned my boards wrong. So I'll move over here. So if I just work that out, actually, this is very convenient to translate this multiple scattering piece into a mass resolution, because the p's cancel. And that gives me a contribution to sigma m that's at this level of 1.4-ish MeV from just taking the sigma theta, multiplying it by p. And that turns out to be the scale of the smallest mass resolution that Babar achieves at low invariant masses. Yeah?
Is the way to interpret this that that would be the error bar on any mass measured?
So it's two things. One is that if you're looking for a bunch of events stacked up at the same mass, because of measurement effects, each one will have a slightly different measured mass. And so you'll have to see that peak over a broader window, which means over more background. So that's the main thing. It's also true that if you see a peak, this is one thing that will go into the absolute knowledge you have of that peak. Now, there's a separate issue from mass resolution or energy resolution, which is the energy scale. And often there's calibration issues there as well that might end up being larger.
And then just to follow up, so would this be the ideal bin width then?
Yeah, so I mean, you can actually do an optimization if you assume a Gaussian signal. How many sigmas do I want my bin to be so that I capture the largest amount of signal with relative to the square root of background that grows linearly with bin size? And I think the optimization comes out to like 1.8 sigma. But this sets the scale. Now, of course, I haven't included that momentum contribution. The momentum contribution is a little bit more complicated because actually I'm going to go into a little less detail than I had in my notes on this in the interest of time. So the way the momentum measurement generally works is that these tracks actually don't go straight because they're in a magnetic field. The magnetic field curves them. And the radius of curvature is, of course, set by the momentum over EB. And you measure, so how do you measure a radius of curvature? Basically, you're measuring what's called the sagitta. How far from straight does my track look between my first layer and my last layer? Here, having a long lever arm is really important because this maximum sagitta goes like L squared over 8 times the radius of curvature. But the uncertainty in measuring the sagitta is basically controlled by the same physics as the uncertainty in measuring, any of these other position uncertainties that we were talking about, right? There's a piece intrinsic from the sensor width that's independent of momentum. And then there's a piece that falls at high momenta that's coming from multiple scattering. And those two pieces basically drive the best tracking you can achieve for momentum reconstruction. So that gives you a sigma p over p that goes basically like an angular uncertainty type of variable times 8p over the length of your lever arm times the size of your magnetic field. So that's why you want big fields, you want a large lever arm. Except now, because you're relying so much on the large lever arm for the sagitta measurement, you're really limited by the momentum uncertainties of your by the position uncertainties of your outer tracker layers rather than your inner tracker layers. And okay, so for Babar, so based on what I told you about sigma theta having a piece that goes like 1 over p and a piece that's p independent, you would expect this, since it has an extra p factor in it, to go like, have a term that goes like p and a term that's linear. And in fact, what Babar gets is something like a 0.2% relative uncertainty plus a 0.13 times p over GeV term, where this is your intrinsic position resolution, and this is your multiple scattering dominated piece. And that can lead to larger mass resolutions than this 1.5, depending on the mass. So notice this fractional delta p uncertainty is going to be more important when you have larger angles, i.e. larger masses. And so at larger masses, this p uncertainty becomes important, and you can get sigma m's. They got to like 8 MeV. So that's kind of the scale of mass resolutions that they have at Babar. And now you can plug all of these formulas in together to get this signal squared over background of order 4. Well, that's just my signal. So let me just write it as S times S over B. So this is like S over root B of order 2. So my signal is the yield I wrote down before. And I'll just use the Babar luminosity and center of mass energy times 1,000 events. Signal over background I get from the formula on the left-hand board. to be this 3 pi over 2 alpha n times epsilon squared ma prime over delta m. And then that delta m is around twice the mass resolution. So I'll say for low masses, I'm going to plug in, I'll call it 3 MeV. I'm sorry for the glare for everybody on the left side of the room. Maybe this eraser will work a little better, maybe it won't. That's my delta M. And that works out to, for MA to something like epsilon over 10 to the minus 3 to the 4th, MA prime over 20 MeV, times 1. Should be of order 4. Not that I've been careful with my order 1 factors here. So that means you'd expect that for A prime masses around 20 MeV, the epsilon sensitivity should be right around this 10 to the minus 3 level, where you have 1,000 events in signal in each bin. That's about the limit that Babar can look for. Now, if I pulled up that Babar plot again, you would see that actually the mass scaling doesn't follow my nice, epsilon goes like at mass to the 1/4 power. It goes a little bit better than that from 20 MeV where they start the search. And then it actually flattens out from about 200 MeV where they're switching over to muons out to many GeV. So one of the things that's going into this flattening out is certainly the contributions of momentum resolution to the mass. But I mean, this is also just reflecting that this was a simplified treatment in many different ways. In particular, the background low is a little bit worse at low masses compared to this irreducible piece. Yeah?
I think I maybe missed what you said. Are you plotting that S squared over B?
Sorry. Thank you. I'm plotting epsilon.
Okay.
That's excluded. And just to sort of calibrate, because I drew this very dramatically, this range here is like a factor of 5-ish in epsilon. So this is like between 2 10 to the minus 3 and a half 10 to the minus 3. I'm not really, so we're not talking about huge effects. But this gave us the right ballpark for sensitivity. OK, so let's see. I have a half hour left. I wanted to switch gears to another signal well, maybe I'll just conclude by saying that so we know by just putting in a remark about luminosity, because we know Bell 2 is going to get more luminosity about 50 times, right? That'll come into this factor. It doesn't come into this factor unless you can improve the mass resolution, which they might be able to a little bit with better analysis, thinner sensors, things like that. But that's not going to improve dramatically. And this yield sensitivity went like epsilon to the 4th. So in practice, Babar to Bell, here you'd expect to improve sensitivity by something like 50 to the 1/4 power. Yeah?
Something I feel like I should probably know as a theorist. When experimentalists claim exclusion, what is that claim? How many?
Good. So it varies from experiment to experiment. Common 90% and 95% are two of the most common ones. But sometimes people struggle to make synthesis plots because they've got a 90% exclusion from one experiment and a 95% from the other. And how do you put those on the same footing? So yeah, this is roughly a 90, I think this is a 90%, but I'm actually not completely sure. Maybe the other thing I should mention is that it is very typical, and they look a little bit different depending on the statistical methods that the group uses. But in all of these narrow bump searches, I drew this line. What the plot actually looks like, it's got all these little wiggles in it. And what that really has to do with is that's coming from the statistical fluctuations. If you have a statistical fluctuation up in the number of events in a bin, you can't set as good of a limit. If you have a statistical fluctuation down, you can set a better limit. And there's a ton of controversy and different prescriptions in the literature for exactly how much better your limit should get. If you had a 2 sigma downwards fluctuation, does that mean that the standard model is 2 sigma excluded, and therefore anything with a signal of 10 to the minus 29 times the standard model, less than 1 event expected, is excluded because the standard model is excluded? That's clearly silly, right? But so there's a couple of different prescriptions in the literature for handling this. Yeah?
So I'm not exactly clear why we see these bumps in something like Babar and not all these other experiments.
You do see them in pretty much, so Babar has, let's see. Every experiment has bumps. I think what you're seeing in this plot is that, sometimes summary plots lose the bumps. And over time, as a result gets propagated through the literature, it has a tendency to get smoothed out by people not using the full data set. And the bumps are suppressed from figures, but everybody has bumps.
I guess they seem like particularly jagged compared to something like NuCal or Charm or anything.
Oh, good. Okay, sorry. So you're right. The beam dump experiments do not have bumps. And the reason is because they're looking for a very different low background signal, as opposed to this bin search. So what I'm really saying is all of the experiments near the top of the plot, the ones that are looking for resonances, they're going to have bumps. Apex has bumps. The Mainz experiments have bumps. Chloe has bumps. Some of them have suppressed bumps in some of the summary plots you see. But the real exclusions have bumps. And then the other thing related to these bumps, you are doing independent searches over, close to 10 GeV in mass with 1 to 8 MeV mass windows, which means you're doing on the order of 5,000 different searches. So there is a huge look elsewhere effect for a signal, which means every one of these papers on a bump hunt, you'll see the statement, the largest significance we saw was a local significance of 3.5 sigma. When we factor in the look elsewhere effect that we looked 5,000 places, we estimate the global significance to be 30%, i.e. 30% of the time you would get a statistical fluctuation that's at least that big. So the threshold to actually discover something in these experiments is significantly higher than the exclusion threshold, because you have up to like 6 or 7 sigma local significance. In other words, the probability of a fluctuation in that bin is at the 7 sigma level before the probability of an exclusion of any such fluctuation in any of your 5,000 bins gets to the 3 sigma evidence level. Yeah?
Could a future muon collider do much better than Bell2 in this kind of search?
So I think it's really, so let's see. Better in terms of epsilon sensitivity would require pretty much, everything I've talked about here carries through. So the question is, are you getting better mass resolution? Are you getting higher luminosity? And are you working at remember, lower center of mass energy actually helped. So a high energy muon collider doesn't give you that much of an advantage here. It actually suppresses the rates for these central dark photon production events. A lower energy muon collider, if it could get up to the inverse Atombarn level, could do something interesting. But I don't think that's a realistic luminosity. And there's no intrinsic advantage to doing muons for models that couple universally. All right, so I want to switch gears now to talk about a completely different signal, but I'll keep the same yield, which is what if we're in one of these light dark matter models, and the dark photon doesn't decay to E plus E minus or mu plus mu minus very much anymore. Instead, if it's heavier than dark matter, it's going to decay into dark matter particle-antiparticle pairs, because its coupling to them isn't given, so I'll call these chi and chi bar, even though they could be any of these pseudo-Dirac or Majorana or scalar models. I'm just going to sort of use a Dirac fermion-like notation. The coupling here is just G dark, not epsilon E. So unless you're in a model with an extremely small G dark, this is going to be the overwhelmingly dominant final state. So now, you don't get a nice E plus E minus pair whose mass you can reconstruct from the A prime. You get invisible. So this is another search that's been done at Babar and will be done at Bell too. This is a photon plus nothing. Now, all you're measuring here is the photon, not the nothing. So you might ask, how can you learn, is there any analog of a resonance search that you could do here? The answer is that you can. If you're looking at full energy E plus E minus pairs coming in, then in the CM frame, you can infer a missing mass squared, which is defined as the CM frame total momentum minus that recoiling photon's momentum. So that should, by momentum conservation, give you the A prime for momentum. Take its 4 vector squared. And in the CM frame, that's just ECM squared minus 2 ECM times the energy of the photon, where the star means in the CM frame. And I told you yesterday that Babar doesn't collide electrons and positrons in the CM frame. For today, I want you to forget that, just because the math's a lot simpler if we work in the CM frame. In the actual analysis, they know the CM frame, they can boost a measured momentum to it. I'm going to pretend that this E gamma star is directly your measured momentum. Yeah?
Wouldn't a standard model process with a final state of a photon plus neutrino, anti-neutrino look exactly the same?
Yeah. That's absolutely right. So you could have this process, right? That's what you're talking about. At 10 GeV energies, this is sufficiently suppressed by the Z mass. This is actually a very rare process. So this is not a relevant background, even though it is an irreducible background. The dominant backgrounds to this process are actually two kinds of things. One is 2 photons, where you miss one of those photons. It just goes into a crack in the detector. If one photon went down the beam pipe, the other photon would have to go down the beam pipe too. So we don't worry about the beam pipe too much in this context. But then you also have this kind of diagram that I drew earlier, talking about backgrounds, kinematically reducible backgrounds for the visible search, where this positron goes down the beam pipe, so you don't see it, and this electron also goes down the beam pipe, and you don't see it. And that's actually the typical thing that you'd expect in these Babar scattering events, right? There's a forward enhancement, but then you could have a wide-angle Brem in the process, and that looks like a single photon plus nothing. So these are the 2 leading backgrounds for this search. They're both instrumental. So how are you going to see this signal? Well, you need to reconstruct the missing mass. And try to reduce these backgrounds as much as possible. Unfortunately, I talked about MEV mass resolutions for the visible signal. These missing mass resolutions are much, much worse. And there's a couple of reasons for that. The first one is that photon energy reconstruction is just not as precise as the momentum reconstruction with a tracker. You're using a calorimeter for this, and that turns out to typically be around 2% of the photon energy at high for E gamma greater than a few GeV. And even worse for lower E gammas. But we'll mostly be interested in be looking at cases where it's at this sort of 2% scale. And then the second is that if you look at this, try to calculate sigma of m miss squared, well, that's 2 m miss times sigma m miss. And that's driven by this sigma E, right? So that's going to be 2 ECM times this sigma E gamma. So that means that the uncertainty in missing mass actually goes like CM energy over missing mass times the sigma E gamma, which was already at the 2% level. But now, if I'm talking about a missing mass of less than a GeV, I get a factor of 10 enhancement on this. In fact, this is getting so big at small invariant masses that linearizing the uncertainties doesn't even really make sense anymore, right? Because you're dividing by 0. So I could just ask what's sigma m miss evaluated at, oh, sorry. I made this look even better, still better than it is. Because that sigma E gamma was 2% on a few GeV, right? So let me go ahead and divide by m miss. Now I've got E gamma over m miss. I can write it this way. E gamma over m miss, sigma E gamma over E gamma. So this is a few percent. These are both large factors. In fact, you can just see for small missing masses that E gamma should be of order ECM over 2. So I've got 2 of these factor of 10 enhancements on a 2% correction, which is basically saying my sigma of m miss over m miss is order 1 for GeV missing masses. So sigma m miss is even the wrong thing to talk about there. You really want to stick to talking about sigma of m miss squared, evaluated at m miss equals 0, which is the missing mass for this process, right? Massless photon. And okay, there we saw we need E gamma of ECM over 2. So that's going to be ECM times sigma E gamma over E gamma times E gamma, which is ECM over 2. So a 0 missing mass of the photon is indistinguishable from a missing mass squared that's about 1% ECM squared, or 1 GeV squared. So one challenge of this analysis is that anything between 0 mass and 1 GeV mass is going to look experimentally exactly the same because it's very hard to resolve low masses in this missing mass channel. Now, if you wanted to look for dark matter, for a dark photon at 3 GeV, resonantly decaying into dark matter, or at 5 GeV, that becomes much easier because the fractional resolution is smaller, and you're looking for a broad bump, but you're looking for a bump over a smooth background again. What you're really dealing with, when you look at the background for this, it tends to look after some sort of, rough set of cuts, loose cuts. It tends to look like big peak at 0, this sort of 0 to 1 GeV. That's dominated by this photon plus missing photon piece. And then a continuum piece that's coming from losing this E plus E minus from Babar scattering that goes out. Sorry, MS. Out to the highest they look at, which is like 7 GeV. They can't look all the way up to threshold just because then the photon gets too soft. This was also the search that I mentioned earlier is a little tricky to trigger on because you have to trigger on this photon plus nothing else in the event. And Babar got all of 50 inverse femtobarns. Compared to 1,400 inverse femtobarns total with this monophoton trigger. So you're going to get lower yields as well. Yeah, question?
What do you mean the photon gets too soft when you go up to its threshold?
So if I looked at missing mass squared of, let's say I wanted my missing mass squared to be 9 GeV. Then if you invert this and solve for E gamma, right, the CM frame E gamma is going to be like ECM squared minus MS squared over 2 ECM. Right, so if this MS squared gets too close to ECM squared, that's going to start getting small. And they could only trigger nicely on photons that had an energy above 1.5 GeV. I think that might even have been their PT. I don't remember if it was an energy or a PT trigger, to be honest. So yeah, does that make sense? Okay. All right, so this is a real problem. This background is a problem for looking at the low mass region. If you have a background that looks like this and you're looking for a signal that looks just like it, but smaller, you would need to measure this background extremely well in order to have any sensitivity to that signal. And that measurement is itself a tricky problem because it's an instrumental background. So the approach that Babar took in a 2014 paper is they designed some cuts that were really effective in rejecting these lost photons at the 50 inverse femtobarn level. In particular, at that level, most of the lost photons were coming from the photon just hitting a crack in the detector. And you could kind of infer, assuming a full ECM, a full center mass energy for the incident state, right? We inferred a whole four momentum for the missing photon, for the missing stuff. So you can ask, if it was massless, what is the most likely place that this photon would have gone? And if that likely place is close to a close to a crack in the detector, you can reject those events. And that was very effective in bringing their sensitivity to these low mass, bringing this low mass background down, with a penalty on signal efficiency that went with it, because they had to cut somewhat aggressively. So it's a little difficult to estimate the sensitivity that you'd get from this kind of search because you have to take into account that tracking inefficiency. But roughly speaking, you know that for my benchmark epsilon of 10 to the minus 3, we had 1,000 events in the full data set. We're going to have something like 30 events in this reduced data set before any cuts. So you might think that this epsilon sensitivity should go down to somewhere between, epsilon of 10 to the minus 3 and maybe, a third of that. So I'll pull up just a few plots from those papers to show you. So let's see. So here is the background after the loose cuts, where you can see the this background coming from lost photons that I showed you, and then very efficient rejection of that background after the tight cuts, but also some lost signal efficiency. And their sensitivity, sorry, this was the 2017 paper, right around the 10 to the minus 3 level. So that's telling you roughly what that they were dealing with signal efficiencies at the 10% level. Yeah. GDark doesn't actually, the only assumption about GDark that goes into this, this limit as a function of epsilon is that GDark is big enough that the branching ratio is essentially 100% to dark matter. So much bigger than epsilon E. And it would only change by order 1 even if it were comparable to epsilon E. So that's what's always assumed in these invisible searches. But now it is certainly true that if you want to compare this to the sort of thermal dark matter motivated parameter space that Philip was talking about, you have to go from a limit on epsilon to like how do I relate this to this Y parameter space? And that comparison does depend on two things that didn't really figure into this limit at all. One is GDark, and the other is the mass of the dark matter. So I think I'll come to that point. That'll be where I start tomorrow. Is how to think about the mapping between these epsilon parameter space restrictions and the thermal dark matter milestones that Philip was talking about. Any other questions?
Isn't this assumption pretty big though, that A prime will always decay to chi-chi bar?
Well, so I think the decays to standard model matter are parametrically suppressed by epsilon. So the assumption is that the dark photon, the assumption motivating this search, right, was that matter kind of reasonably strongly to the dark photon. Is that like an alpha coupling, like similar to electromagnetic, or is that stronger or a little bit weaker? I think that you should be kind of agnostic about. But if this epsilon is 10 to the minus 3, then you need an alpha dark of like 10 to the minus 7, way weaker than anything we've seen in the standard model, in order to have decays to visible signals be comparable. Let me actually put the answer a different way, which is that as an experimentalist, you want to make sure that your experiment is sensitive to the two complementary possibilities. Either the dark photon, which in the simple model with just a dark photon and dark matter, and the standard model, there's really only two possibilities. Either it decays back to the standard model, or it decays to dark matter. And they've checked those two off. Now there's another question you could ask, which is what if the dark sector is complicated, maybe as complicated as the standard model? Or these strongly interacting models that Yonit was talking about, for example, they have resonances in them. What if the dark photon decays to those resonances instead of directly to the dark matter? And so I think the biggest loophole to this invisible search plus the standard model final state searches viewed together as a collective unit is the possibility that the dark photon might actually decay into a more complicated dark sector. And then you have to look for more complicated signals in order to see it. There's one class of experiment that's kind of tailor-made to deal with that possibility, which is basically looking at this same reaction, but in a fixed target experiment. So you look at a positron beam hitting atomic electron targets. and then measure this, do the same missing mass measurement, but now you can do a sort of smaller, basically, you could even do this in principle at a collider. It's just difficult to trigger on. Do the missing mass measurement without requiring that the dark photon goes to nothing. Require that it goes to something that includes a bit of missing energy, but doesn't have to be completely invisible. The trigger for this analysis required no tracks. So if the dark photon decayed into dark matter, but there was like an excited dark matter particle that then produced some E plus E minus with sizable energy, large splitting inelastic dark matter might not get through that trigger. And this search actually wouldn't be sensitive to it. So you want to do something more inclusive, ideally. The challenge is, can you trigger on a hard photon plus maybe some other stuff? You have to really think about how do you define maybe some other stuff in a way that the standard model rate is small enough, so it's a useful trigger, but that it would capture a lot of your dark sector physics. So this is something that people are thinking about both in fixed target searches and actually at Bell 2, looking at monophoton plus stuff. And then for there's other cases where the dark photon could decay into a more complicated visible state. So for example, and Babar has actually done, when Babar was running, they were mainly a B-physics experiment. Now that a lot of the B-physics results have been extracted, I would say a large fraction of the remaining Babar collaboration activity is actually focused on thinking about a range of different dark sector signals, and they're continuing to do a lot of analyses, looking for these sort of more exotic possibilities. Things like, what if you have a new gauge boson that couples only to muons, and then you would see it bremmed off in muon final states? Or what if you have some non-abelian sector where that dark photon decays into dark W's, but then there's no custodial SU2 in the dark sector, the dark W's decay to E plus E minus or mu plus mu minus, and you look for a 4-lepton final state with invariant mass resonances. There's all kinds of different scenarios that you can look at, that any one of them, it's easy to say, oh, come on, do you really think nature works like that? The answer is probably not, but if we look for enough of them, we might get in the right ballpark to find something. And so there's actually a lot of effort going on for these more general cases in Babar as well. But I wanted to focus on the two sort of most minimal signals that you would expect from dark matter, or from basically a simple dark sector where the mediator is the lightest thing, or where at least dark matter is, and this is the other thing, if dark matter is one of the things it can decay to, and it can also have like 5 other comparably big exotic decay modes, then it's still decaying to dark matter 1/6 of the time. And this is still a really good way to search for it. Any more questions? All right.
I currently have scheduled for 10:30 to 6.
Perfect.
Okay.
Yeah, that's
I think other people said they got in.
Nice lecture.
Thanks.
Are you guys interested?
Um, well, I lost Philip, so I think I think he wanted to go home for lunch, and well, we had to eat at our place where he was also, I don't know, he might have actually gone to, let me see. It's possible he went to pick up our daughter already.
Oh, you have your daughter for lunch?
I have no.
Stefania and I are both sick of the cafeteria.
Uh-huh. Yeah. Yeah, so our daughter's been jet lagged and cranky. Um, yep, so was gonna maybe try to pick her up early from camp today, and I don't know if he's already done that. Although I need to check with him to see if.
We're also
Yeah.
Hi. MIT colloquium a couple years ago.
I think 4 years ago. It might have been more recent. I don't know. Okay. Was it virtual?
Yeah.
Okay, yeah, I think I gave a virtual MIT colloquium more recently than that, yeah. So, well, yeah, that would have been the last 2 years for sure.
I was curious if you're going to be talking about any of the stuff you've been doing recently, maybe during your last lecture.
I think so, yeah. I'm going at about 80% of my usual speed. We'll see how much time I get to cover it, but yeah, that's my plan. Kind of trying to the dark matter signals and visible signals, and just kind of so that I can kill two birds with one stone. But yeah, I'm hoping I'll get to that. Now, more recent, I am planning to talk about like LBMX and the light dark matter, the missing momentum idea. If you meant like direct deflection or much more recent stuff, no, I wasn't planning to.
Okay, well, I was going to say if you have some chance before, if you have it like some time before you leave, I'd definitely love to.
Okay, yeah. So I am trying to figure out, so today might be the best time over lunch, but I'm trying to figure out, so tomorrow around lunchtime, we're both going to pick up our daughter early from camp and just like do some hiking, because she's, yeah. Philip and I are married, we have a kid. She had to come with us. She has to go to camp, and she's also jet lagged because she wants to stay up until 10 every night because she's used to California time.